Hey, a bunch of you guys had asked for more practice or more help on the equations. So I know we did this one in class, but I wanted to go through these again just so you can see how we do them and take it at your own speed, pause me, whatever is going to be helpful for you. So let's give this a try. So the acceleration equations are all found in this triangle, so whatever thing you need, you cover it up, and then you look at the other two things and how they're related. So if they're next to each other like this, you do times. If they're above and below, you do division. So acceleration equals F net divided by m, mass equals F net divided by a, and F net equals mass times acceleration. And what that really means is that like whatever is above has a direct relationship to acceleration, for example, and whatever's below has an inverse relationship to acceleration, for example. So direct relationship, as there's more force, there's more acceleration. Inverse relationship, as the mass increases, the acceleration decreases, right? Okay, so a man hits a golf ball 0.2 kilograms, which accelerates at a rate of 20 meters per second squared. What is the net force acting on the ball when the club is hitting it? So the equation you're going to use, since we're looking for net force, is going to be F net equals mass times acceleration. And so our mass is 0.2 kilograms. Our acceleration is going to be 20 meters per second squared. So 0.2 times 20 is going to be a net force of 4 newtons. Yes, buddy? Okay, so here we go on to number 2. Okay, so for this one, the wind pushes a paper cup along the sand at a beach. The cup has a mass of 0.025 kilograms and accelerates at a rate of 5 meters per second squared. So how much force is the wind exerting on the cup? So easy peasy, we need to know force, and I see our mass right here, and I see our acceleration right there. So we're just going to do force, F net equals the mass times the acceleration. And just like we have, like if you can imagine this as 1/4, if we do 1/4 times 5, it's going to be $1.25. So 125 right there, newtons, 0.125. Okay, so next one is you push a friend sitting on a swing with a force of 200 newtons when they're sitting at the very bottom of the swing's arc. They accelerate at a rate of 4 meters per second. Find the mass of your friend. Sorry, it's like really late. Okay, so we're looking for mass. So if I cover up m, it's going to be F net divided by acceleration. So the net force is 200 newtons. The acceleration is 4 meters per second squared. So I just do, I'm looking for mass, F net divided by acceleration. And that gives us, and you can also do this in your head, you can think what's $2 divided by 4? That's going to be 50 cents each, right? 50. Okay, and next one, a carpenter drops a 1.5 kilogram hammer off the roof of a house. The hammer falls to the ground with 15 newtons of gravitational force pulling down on it. Assuming there is no air resistance, what was the acceleration of the hammer as it fell? So we're looking for acceleration, and I see we have the net force right here, and we have the mass right there. So we're going to do net force divided by mass, and that's going to be 10 meters per second squared. And again, you can kind of see this happening because we have 1.5 and we have 15, so that's going to be a multiple of 10 there to bump that decimal point over. And almost done, getting close. Okay, Peter's car ran out of gas. He is pushing his car down a level road at a constant velocity of 0.5 meters per second with a force of 243 newtons to get to the gas station. What is the total force acting on the car in the opposite direction? Now this is a trick question, and I'll tell you why. Okay, so the trick to this question is that he's traveling at a constant velocity. And when there is a constant velocity, that means that the forces are balanced. So the amount of forward motion is the same as the amount of resistance motion, which is allowing it to move forward but not to accelerate, right? Or decelerate. It's just moving at a constant velocity. So the forces are balanced. 243 newtons of resistance force balancing out his 243 newtons of forward pushing. Okay, last one, because I have another video that I made that goes through 7 through 10. A 1,200 kilogram car is traveling at 13.9 meters per second velocity. It experiences an air resistance of 5,000 newtons and a road friction of 7,500 newtons. If the engine and wheels push the car forward with a force of 17,500 newtons, what is the car's acceleration? So, force diagram looks like this. I have air resistance, 5,000 newtons, road friction, 7,500 newtons, going in this direction. And then I have an applied force from the engine and the wheels of 17,500 newtons in this direction. So, in order to figure out the net force, I can add all those together. So I'm going to do 7,500, well, it's adding these two together because they're going in the same direction, and minusing them from this one because it's this force is going to cancel out the force in that direction to that in that amount, right? So there's still an excess of 12,500 newtons, and that's the net force there. So now I want to solve for the car's acceleration. So for that, I'm going to do acceleration equals F net divided by mass. And, sorry, it's super late. Okay, so the net force is 12,500 newtons and the mass is 1,200 kilograms. So I just do F net divided by mass, and that is 10.4 meters per second squared. And again, this is something you can do almost in your head because you can see that this is like 12,000 newtons and this is like 1,200 newtons, right? So it's going to be a difference of 10, like it's a multiple of 10, I guess is what I'm trying to say. And then that 0.4 is where that 0.5 comes from, okay? So yeah, check out the other video for 7 through 10, and good luck on the test on Friday and Monday. You guys are going to do great. Okay, bye.